Hi everyone, I'm Mark Smith with Macroscopic Solutions, and the tutorial video that I'm about to show you is going to be about handling a large volume of different data in order to batch process a large number of models within Agisoft Metashape. So typically, before any time that I've shared a tutorial video with you, it's been a complete walkthrough from the imaging process into processing that data, and then ultimately moving that image data into Agisoft Metashape to generate a final output model. In today's example, what I'm going to be doing is taking a lot of data and aggregating it into one location so that I can generate multiple models automatically through a more standardized or more seamless workflow. Now, the samples that I'm going to be using are both challenging but also quite interesting to share with you. They are going to be the images of the root structures of the Arabidopsis plants that were grown in zero gravity in space. Now, these samples, 12 of them total, were launched on the Polaris Dawn mission via a SpaceX Falcon 9 on September 10th, 2024. The crew that remained in low Earth orbit for an extended amount of time conducted several scientific research studies and experiments on board. Among them was the U.S. Air Force's root study. Now, of the 12 samples that went up into space, 6 of them went off for gene sequencing. The other 6 were scanned and imaged. And now what we're going to be doing is we're going to be taking the image data that we captured for each of those samples, and we're going to be generating a 3D model of those root structures. Now, we also have image data of those cuvettes and the root structures before they were ever sent into space. So in time, we're also going to be generating models for those. We also did several ground studies experiments. So this is where we had an additional 12 Arabidopsis plants grown over the same time interval, but they remained on Earth. So that way, we can then compare the results of the ground control experiments with the plants that were grown in space to see if there are any fundamental differences in structure or growth pattern and so forth. So it's kind of a neat study. It's one that's going to be repeated. Since the Polaris Dawn mission launched, this study has been repeated on the International Space Station about a month later. And there are future experiments going up in space which will involve things like tomatoes and other types of plants as well. So stay tuned. Over the next couple of years, there's going to be more launches and more research in this area, and Macroscopic Solutions is really happy to be a part of that. But for now, what I'd like to do is turn to the data that we have on the computer. I'm going to show you how we have it organized and the steps we're going to take to refine the data and ultimately generate those 3D models. Okay, so I just want to show everybody what we're working with. At the moment, I have my directory open where all of my source data is stored. These are the images that have been captured with the Macropod PRO 3D and then stored according to each individual sample. So I have my ground control samples. These are the samples that were captured and remained on Earth to be compared with the samples that were sent up in space. I also have the ground control dailies. So this is every single day for 14 days. They were re-scanned, re-imaged. We're going to try and 3D model those as well. And then we have the Polaris Dawn pre-launch. So this is all of the samples that were imaged before they went up into space. And then, of course, we have the Polaris Dawn space experiment from after they came home from space. So to give you an idea of what we're working with, I'm just going to open up a pre-launch, open up this first packet here, and show you. So this is the Arabidopsis plant coming out of a clear agar that's been stored in a plastic cuvette. We can't use glass because these went up into space. So we're working with some limitations here. One is we have an agar that is clear, but it's not so clear. It's not like water clear. So we have that challenge ahead. We're also dealing with a cubic container, which means that we're only seeing a projection of the sample inside because we're looking through a clear plane that is in only one image parallel to the lens, but in most cases it's oblique. It's at an angle, which means that there's going to be an optical shift. So 3D modeling this is going to be quite challenging for that reason. We can also see kind of how this looks. I want to show you how they look before and after, because after these samples came back from space, we had to flash freeze them. and that corrupts the agar a little bit. What it does is it clouds it, and it causes the roots to go out of focus. So we don't need absolute clarity. We really just need structure, because all we're trying to do is 3D model the root paths. And we do have good image data showing what the roots did as backups. But of course, yeah, we want to get good 3D models of every single sample. So let's now go down to the Polaris Dawn space experiment. So we'll look at cuvette 1, and we're going to open up one of these samples. You can see how cloudy the agar has gotten. This is after the samples have gone into space. We weren't exactly sure what we would expect, but also we weren't sure what we were going to expect after we flash freeze these samples. Now remember, we're only working with 6 of these images, or 6 of these samples. The other 6 were sent off for gene sequencing. So every other cuvette, so position 1, 5, 9, 2, 6, and 10, those are the cuvettes that we're going to be modeling. You can see each one is slightly different, but you can see again how cloudy that root structure is. So what we're going to try and do is 3D model these without any editing. We're going to pull all the data in, we're going to do a batch process and see what we get. If we learn or see that it's not effective, then what we'll do is we'll go into Photoshop, we'll perform a mass edit and apply it to the rest of the images in the data, and we'll try it again and run it that way. Luckily, the computer that I'm using is quite powerful. I'll just kind of show you what the spec is at the moment. So the process should go fairly quickly. So about this Mac, I'm not sure why that happened. So I'm running 3.2 gigahertz 16-core Intel Xeon. It's a 2019 Mac Pro with an AMD Radeon 32 gig Pro Vega 2. And I have 512 gigabytes of DDR4 memory. So quite a bit of computing power. So hopefully the process should go pretty quickly. But there's going to be some times when I'll step away while the computer is processing, and then I'll come back. What I'm going to be doing when I transfer all the data is I'm really just going to have the day 1 image, and I'm going to 3D model those. And then the day 14, so 2 weeks later, that image data is also going to be imported. So as I go through and I create a chunk, you can kind of see, then I'll pull in all the images associated with that chunk. So I can see those here. I can kind of inspect, if the flash didn't fire or anything, and I can edit those as needed. Do the same thing here. You can see it looks really good. Same thing here. And you can see I've got pretty good data there. And as I'm kind of going through, I'm ticking off the list, and I'm just right-clicking that it's complete, that I know that it's been imported. So I just put a little green notification there just to keep me organized. So basically what I'll do is I'll add a chunk, rename that chunk, the directory name, pull in the image data, press OK, and kind of inspect. You can see here, this is an image where the flash didn't fire, so we're just going to get rid of that. And all the other images are good. Again, mark it green, move on to the next one. I probably won't show you this process for every single image because it's going to be somewhat time consuming. But what I'd like to do is at least show you the steps that I'm going to be taking so that they can be replicated. This is a perfect example. This one's exactly from front on. We can see our root structure through there. It's very good. So what I'm going to do is I'm going to open this up in Photoshop, and any or all edits that we make to this image, we're going to be duplicating or applying to the rest of the imagery that's in that directory there. So what we want to be doing is recording all of our actions using a history function. So in here, I'm going to go to Window, and I'm going to activate the History tab. So History is going to show us any types of edits that we make. We also want our actions to be found on here. And what we'll do is we'll create a brand new folder. This will be called Polaris Dawn Edits. And now we need to create an action. So the action will be root isolation. So that's the goal. We're going to be basically trying to edit these photographs so that the root structure is much, much more prominent rather than the plastic of the cuvette or the color of the agar. So What I'm first going to start to do is really mess with contrast. So I think curves is definitely the best place to start. You can see here, so just by lowering the bottom part of the curve upon this histogram, we can already make that agar much, much more darker. And if I move this line up here, this should theoretically make the root structure much, much lighter. And you can see that that's happening. We could also probably try and create a negative or even just work off of a black and white image and then hyper contrast this thing just to isolate the root. But I'm worried about other cuvettes where there might be much more faint root structures that are popping off that we might start to overprint. So we want to be dramatic, but we also want to be subtle so that we're not actually eliminating information that's quite valuable. What I'd also like to do is look at the channels. I'd like to see if the white that we're seeing has any colors that perhaps the cuvette does not possess. So just by sort of taking a look at the different color bands, we might be able to somehow get something that's a bit more hyperspectral. So you can see, like, here everything is turning pink, but perhaps what we can try and do is maybe there's some spectral data that's located within the root where, you know, this process might actually turn it green while the cuvette might stay or remain pink. And that is plausible. So you can see here the agar, now we're starting to actually, you know, find some blue, whereas other reflective areas are highlighted much more pink. So that's really the goal, is to see if we can create two different colors, which will make the 3D modeling process much more simple. Okay, so this is kind of what I'm going for. So you can kind of see that the agar has now been turned into this pink, and the root structure is now a little bit more like a baby blue. Now, the cuvette as well also has that baby blue characteristic, but it's far removed from where the root is, which might make the 3D modeling process a little bit more simplified. So this is actually promising. So what I might do now is just record the values, because these values can probably be replicated in other images so that we can sort of fully automate this process for all of the images. So right now we're on our red channel of our green and blue, and of our sub-red we have minus 198%. I'm just going to jot a note, plus 178% for green. Blue is plus 96%. Okay, now we're going to switch down to green. So this isn't necessarily hyperspectral imaging. We didn't use a hyperspectral camera at all, but we still have a good amount of spectral data that we can play with in order to achieve a specific result. And this specific result is merely just the structure of the root. That's the only thing that we're interested in. We don't need color accuracy. You know, color is not what we're after when it comes to this root, and we still have, let's just say we were interested in that information, we still have the original photographs to base that off of. So it's not necessarily important for the 3D modeling portion of this study. Okay, so I've jotted all of these down. What I might do is just kind of mess with the blue a little bit more to see if we can get it. Yeah, see, that's a little bit more blue, and there's a bit more contrast there. So I might bump that up to 151%. Okay, so we'll stop messing with the colors. Now what we might do is go back to our contrasting tool. What we want to do is see if we can again make that pink area a bit darker. And we want to keep that root structure really vibrant. Yeah, so you can see that's really quite vibrant. It's almost fluorescent in there. Okay, that's pretty good. So now I want to go back to curves. You can kind of see the background is a bit more blue than it is black. So that's all I'm aiming to do now. I want to keep that root kind of the same color, and I just want that background to get really dark, almost less blue. Okay, so that's pretty good. So now that we've done that, the next thing really is to sort of test if we get the same result with all of the other image data. Okay, so I'm going to duplicate the Polaris Dawn space experiment folder. So just going to copy, and then paste it out here. And we'll just call it duplicated. And I'm going to move that back into our main Polaris Dawn folder. We're going to open Photoshop back up, and we're going to navigate to scripts, which is how we're going to be able to apply the edits to all of the individual images. Okay, so File, Scripts, and Image Processor. Okay, so this was the root isolation under Polaris Dawn Edit, so I have that down here in my Run action. I need to select the folder, which is that duplicate folder that I just created. So duplicated. You can run all of them, and it might work. You can include all subfolders, but sometimes it has a high failure rate. So I'm just going to do them one by one. I'm going to start with cuvette 1, position 1, open that folder, press open. Now I have the option to save in the same location. I can set up the directory however I need to. So I'm just going to save it in the same location and then save it as a JPEG and run this batch. So you'll see now it's going to pull each individual original image. It's going to apply those edits. And if I navigate back to the directory here, under duplicated, you're going to see a new folder being created. It's called JPEG. And now you can see those techniques being applied to all of the images that are contained within that folder automatically. So this is just a kind of a fast way to achieve this automated task. And we're going to do this for all of them. And we're going to import these images also into Metashape just to see if it produces a different result or works better for us. So we can almost kind of do a side-by-side comparison. All of our data is now uploaded into Agisoft Metashape. This includes the ground control, the samples that were sent to space, and the recently color-corrected 6 samples that returned from space after being frozen, just for high contrast. So, if I were to click on any one of these, you can then inspect the images and the photos corresponding to each of those samples. The next step is to make sure that the lens information is correct. So for each of these, so what I'm going to do now is minimize the main directory, because now all of our data is in Metashape. I'm also going to hit that save button there just to make sure that I save my work. This is a lot of data. Sometimes your computer might not be able to handle all this. It's always good to save your data and save your work real fast, or at least your progress. Okay, so what we want to do is hit Tools and Camera Calibration, and unfortunately you can't do this for all of them, which is kind of a pain, which means I have to go through and single-handedly do this for each one. But basically we're going to change the focal length here. So alter that to pre-calibrated, change it to 20,000, and that's because we used an adapter on a mirrorless camera in order to sort of extend this. So I find that the images are aligned better if you change this focal plane to 20,000. The other thing is we have some fixed parameters. The camera's in a fixed location, so we can go ahead and fix CX and CY axes and press OK. So now this is going to be kind of a tedious process. As I said, I have to do this for all of them. So let me go through, finish these up, and then we will move forward with our batch. Okay, all of the lens parameters have been fixed. So now we're ready to go ahead and get started with our batch. We're going to navigate to Workflow, Batch Process. Okay, we want to make sure that all chunks are added and they're all selected, and we want to align photos in this step. We can proceed later on, but I want to do one step at a time. We're going to keep all settings fixed to their presets. We're not going to change anything. We're going to hit OK, and then we'll inspect the work when it's all finished. But right now, we're just trying to align the images accurately. So we can go ahead, we can hit OK, and let this process through. Also worth pointing out that, yeah, once we process a batch, we can also see that this particular job, we can see where we are in the process and also if there are any that had failed. But this should, I mean, this is a lot of data here, but again, the computer's pretty powerful, so I wouldn't imagine that this would take more than an hour, maybe more than a couple of hours. But this is one of the more time-intensive processes here. Okay, so the initial alignment has finished, but one thing I noticed is that, well, not all of them are perfect. One of them actually failed, so that's actually pretty good. I mean, of all the ones I had to actually align with only one failure, and I found out the only reason it failed is because the image data, for some reason, it wasn't sourced. I guess somehow it got relocated in the directory, so it's a pretty subtle problem. But as I go through these, there's a few that look like they're not great. Here's a good example. So I just wonder if we can, let's see, I wonder if you can, well, we'll just kind of go through these one by one. But basically what I'm going to do as they fail is I'd like to get rid of these edge-on viewpoints. So you can see here, because we're looking at it right into the corner, we actually have our root duplicated. So in a way, these images really have no contribution to the model. So sometimes what you can do is get rid of these really highly oblique images. So I'm going to select these. I'm going to remove those cameras. I'm going to go down to the next point of rotation, so probably about here. Actually, probably more like here. And then we're going to remove that round of images. And you can see it's basically cutting out about 13 at a time. We just kind of want to find that that break again. Here we go. So at this point we're starting to see the cuvette from its corner. We'll remove those images. And likewise right about here we're looking at it as a corner as well. So we'll remove those. And now what we want to do is, you know, if ever you have a model that didn't come out too great, let me see if I can, so what we're going to do is go back to workflow. We're going to realign those models, reset the current alignment, and we're going to align that one more time. Okay, I'm just going to update everybody on what I've been doing. So all of the data that I pulled into Metashape has processed. Basically, I wanted to align those images. There are a few that I had issues with. So I initially had issues with about 8 of the individual batches, but the rest of them actually came together really, really well. So for example, if I click on any one of these, you'll see all of the images are aligned in a perfect a perfect circle around the subject, and all of these are pretty much the same. When it comes to the other ones that I was having issues with, I was rerunning them, and I reran them and then had more success. So about 4 of the 7 actually came together really well, and again produced a similar result to what you see here. Now, just to kind of recap how you would go about reprocessing all of the data. So you can see there's still 4 I have issues with. There's this one where you don't see an arrow. There's this one where you don't see an arrow. This one, and this one where I actually just kind of experimented a little bit. So there is data here, and I'll explain why in a second. But let's say I needed to rerun these 4, and let's just, you know, for the sake of argument, say that the images are still in here. All you would do is go to Workflow, Batch Process, and you can see what I'll do is I can just create a new job. So I would remove that job. I'd add a new one. I want to select unprocessed chunks because there's only 4 that I need to select to process. I want to align photos, but now I want to actually hit a selection. So here it's the ground control 9073, and then we have the 210 mutant sample 7. That's here. The 907 wild type sample 1 here, and the 907 sample type 5. So really those are the only 4 that I'm having issues with. To reprocess these, you need to reset the current alignment. You can't have it build off of the prior alignment. You need to start from scratch because it didn't come together well. So you just double click here, change that to yes. And in order to get a lot of the prior models to fit, what I've been messing around with is the key point limit. I actually bumped this down to 60,000 and the tie point up 1,000 to 6,000. And that actually did the trick for quite a few of them. So this is how I would go about reprocessing this data. You would just hit OK, and it would run into this batch here, and you press OK when you're ready to go. But I'm not going to do that right now. I just wanted to sort of show you how to reprocess failed batches. The next step that I did is I realized that the images that were in here were actually kind of dark. You can see now, so if I were to click on this is one I'm having a problem with. This is actually images that I recently brightened. So I have one open in Photoshop. You can see how dark it is here. I think that's contributing to the reason why the model isn't coming together very well. So what I did is I actually recorded my actions of root isolation number 3, and I beefed up the contrast. So I changed the levels and I changed the curves so that the cuvettes would brighten up a little bit more. Sorry about that. I was trying to actually show you how it looks after I process an image. So I clicked on what is that? That's 0714. So here's the processed edited images. I'll open up that same image that I ran through scripts, and you can see here how much brighter that is. The root's more prominent. The number, which can be used as a good identifying mark, is not here. I'm also realizing that the stage, where normally I have red, blue, green, and white edges, for some reason this particular stage doesn't have those marks, and I'm not sure why that is. That could also be contributing into why this didn't come together very well. I must have switched those stages. A lot was going on. It was a lot of work at the time, so something must have happened there, or the colors just wore off through time just from handling. But in either case, we'll still get through this. What I have done is I've rerun all of the images where I reshaped the contrast, and I did get a result. So this is the result here. It's still not exactly perfect. You can see if I were to just zoom into this, it's a lot of data, so it's going to take a second. We're zooming out first, but you can see some of the images over here in the back are, kind of misplaced. So I just need to double check why that is, and then we can run it again. But yeah, for the most part, that's a much better result than I was getting. So good news there. So I'm going to do the same sort of process with these other 3, and then rerun it, and then I think I'll actually be okay. But what I also want to do is, we're coming up at 7:13 p.m. So to make good use of my time overnight, I now want to take the files that did run really well, and I want to move on to the next step. So what we're going to do now is go back to batch process. All right, we're going to remove build model. We're not ready to build a model. We want to build our point clouds. Again, sorry, we're going to deselect these items. We're going to save for later. So I'm guessing I can't do anything with this. So I'm guessing it's going to default to using the point cloud data on its own. Change the quality to high, uniform sampling, point spacing. You could actually change this to 0.05 to get an even more dense point cloud. Depth filtering, calculate point colors, yes. Replace default point cloud, no. Okay, so I think we're good to go on that front. So now what we're going to do is we're going to press OK, and now we're going to basically make this low density point cloud one that's very dense, and hopefully we'll catch a glimpse of what our model is going to look like because our points will be so closely compacted. The next step after that is to just inspect the root, see how the root looks, combine it if it's been, you know, sort of segmented into different regions, and then we might even, depends on whether or not we're actually going to build a model in Agisoft. It's possible we might actually just move it into Blender and draw a line through our point clouds and then build models that way. Again, we just need to understand the trajectory of the root. So there's a couple different ways we're going to go about doing this, but for the most part, I'm just going to process this batch, and hopefully you get a good idea of how to batch process you know, a large data set like this. Okay, in a way, we're going to be picking up exactly where we left off. Couple things though, I did plow ahead because I needed to have some of the deliverable results to the United States Air Force in time, so I didn't necessarily have time to record every step. So I will just kind of let everybody know that I did move forward in processing all of the files. They're all aligned now, and I have dense point clouds, and I actually have models for all of them. So basically what I'm doing is I'm going back to one of the problematic samples, the ones that one that I had a hard time aligning. And what I did is essentially the exact same thing as before. I edited the brightness of all of those images, re-imported them, and then went to align the data, and it came up just fine. So that's where I'm at. So essentially, we're picking up exactly where we just left off with it, which is from a low dense point cloud to a dense point cloud. Okay, so bringing the model center, just gonna center everything. You can get a good view of the alignment. Again, this is one that I was having a really hard time with. I don't know why. This one chose to give me a hard time, but you know, since re-importing the data with a little bit of Photoshop, you can see, you know, even in the low dense point cloud, I'm making out the plant and I'm making out the root structures down here. So let's just go ahead and show everybody what a dense point cloud looks like. Also want to share with you that in the time period between sort of the last changeover from the last frame, there's actually been a significant update to Metashape, which I usually love because updates are usually associated with a significant boost in performance, and that is true. You can see in this dense point cloud, I have my roots very well defined, and this is actually a much better result than I was getting in the prior version, at least at this stage. Before, I was getting a lot more noise. I'd have to do a lot more work to clean these up. This is very minimal, so that's a win. So this is what I basically have every single time I have built a dense point cloud for these cuvettes. I have 4 representations of the exact same pathway that the root has taken through the agar, and that is simply because of refraction. So as the lens is looking onward, like right through the glass, as long as this face here is perpendicular to the viewing direction, then my root is in the perfect orientation. But as the cuvette rotates 2 degrees, there's an optical shift because of optical refraction where the root is now repositioned. It's kind of like looking at a fish obliquely through the surface of water. It's actually, you know, it's a few degrees away from where you're viewing it. So there's a couple of different methods in terms of cleaning this up, but for the sake of just getting a point cloud finished and getting it to the client, all I've been doing is isolating the most prominent looking root structure, and ideally that's the one that's closest to basically that facet of the cuvette. So I'll crop out that section of the root, and then we'll clean up that section of the root. The top is a bit irrelevant, that little overhang. That interface between air and agar is going to be really difficult to reveal that pathway, so it's not one we're so concerned about. We're really concerned about what the roots are doing at depth. But I leave them just in case it does actually give us some data about where the root has come from relative to the actual plant. Okay, so that's essentially what I've been doing in terms of a deliverable. So I have a really well-defined point cloud. It follows a pattern in all directions.
a lot of times what's happening when you see a plane where it starts to flatten out as you rotate, you can see there's still bends, but generally what's happening is the root is sort of, it's basically progressing along that interface, and then once it finds the facet of the cuvette, then it basically shoots itself downward in between the aggregate and the plastic of the face. So some have come out really flat, others look very different. You know, but that's something that we're going to be looking at in terms of, you know, and answering the question why in time. But for now, just showing you how I generate this point cloud. So another thing I've been doing is, because these point clouds are very good for us, I can actually take this point cloud, pull it into Blender, and actually reproject the pathway that I need, which is something I will probably show in a different video. I realize this video is getting kind of long, but I will pull these into Blender. So usually at this phase, what I'm doing is I'm exporting a point cloud. So this is wild type sample 1. So I have this point clouds and models here. And this is 907 wild type sample 1. So I'll just expand. Should be this one here. Yep, there's nothing in there. So I'll just enter a 1 just for now. That way I don't have to write out the whole name. And then I'll go to where I just saved it. So that's 1. That's this right here. And I'm just going to overwrite that 1. Okay. So now you can see for all of my data, what I've done is in this folder, I've created something called point clouds and models, and I've been exporting individual point clouds for each of the corresponding folders. So all of my data is now here. The next step is to triangulate the points and create a model. Now it's not going to be perfect because there's no data on the back side of this root. There's only data up here. So now, just at least to have that visualization and triangulation, we're going to batch process that again. So in order to batch process, just like before, you're going to add all of your data, and it's going to correspond to all the point clouds that we have. And we are going to be building a model. And the model for this, we're not using depth maps. We're going to be using the point clouds. And there's nothing else to change, so you can press OK, and then press OK, and they're going to continue to process. Now I'm clicking on Ground Control 210 Mutant Sample, because this is a point cloud that I have triangulated. And you can see here, this is our root. We have a very good model from that one facet. You can actually see it even has the curvature and it has the texture that we're after in that root. But there's a lot of triangular noise outside because, again, the backside is incomplete. So we want to clean that up a bit. And just like we did with our point cloud, you're just going to follow around the root structure. And we're going to do a crop function. And we can keep getting closer and closer to this just to refine it a bit more. So get a little bit closer to that root. Okay, and that's what we're left with. So this is how we create a model from that root. Now, admittedly, it's not a perfect model because we have the challenge of shooting through cuvettes. However, it does give us the general pathway that the root has taken as it was grown in space and on Earth on the ground control experiments. So that's pretty cool. So one thing we can actually do now is move this over to Blender, and we can trace basically the region of most dense points and create a line and then expand that line, and then we have a visual representation of that pathway in three-dimensional form. This is something that actually Major Travis Tubbs with the United States Air Force had done after my last demo video that I posted online, and it's something that I actually do not know completely well, so we're actually going to sit down together and we're going to try and figure out how he did that on the old model in order to actually show the pathway here. So I just noticed how long this video is getting, so I don't want to make it too long. I kind of want to keep this YouTube video focused on the purpose, which was batch processing. So what I'm going to do now is I'm going to stop the video here, and then in a future video, what I'm going to do is actually generate the model in a more accurate fashion. So it's more time consuming, but in this way, we're actually going to get a much better result. So I'll just sort of briefly explain what the next video tutorial is going to be. Basically, I'm going to append different chunks over the same chunk. So what I've done is that same route that we just 3D modeled, or generated a point cloud for, and 3D modeled, I'm now going to be utilizing all 4 pathways as sort of drawn out from the different facets on this cuvette. So as before, where I just took the information that you can see highlighted now I've gone back to the dense point cloud. I'm going to eliminate all the noise, and I'm going to get all 4 of these root pathways to merge to generate one good file. So I'm not exactly sure if that's going to work out the way that I intend, but there is an appendment method that I'm going to be showing everybody how to use, and I think it's going to be beneficial because I think, at least for me, it's been a common occurrence where I've had something where the photos were misaligned. However, the 2 point clouds that were output were good. They were just mismatched or in the wrong location. So that future video is going to show everyone how to merge those 2 without the use of markers, which is sometimes pretty inaccurate. So stay tuned for that. Also, in another future video, I'm going to be taking these same routes and I'm going to be showcasing how we can trace the pathway in Blender. So that'll give all my viewers a little bit of Blender background as well. I was going to include that in this video, but again, I think it's getting a little long, so we're going to cut it here. So again, thank you for tuning in. I hope this was informative on batch processing in Agisoft Metashape. And stay tuned for those future videos. I look forward to sharing that with you.